Hi everybody, my name is Valentin Andrei and I'm a performance and capacity engineer at Meta. My main focus is software optimizations across the AI training fleet, building observability and tooling for deep dive performance introspection. Together with my colleagues Riham, Hao and Lee, we are going to cover the highlights on how we provide AI observability at the Meta scale. The agenda includes details about our telemetry systems, tools that we use to deep dive into the performance of an applications, and how we use performance observability infrastructure to maximize the return of investments of our optimizations work. The problem that we're trying to solve is how do we keep infrastructure costs in check in the context of exponentially increasing demand? And in hyperscale companies, there are many factors that increase our infrastructure costs. You can consider cost as maybe dollar amount, energy usage, or carbon dioxide emissions. And the factors that increase these costs are maybe larger models, we hire more ML engineers, we use larger data sets, and we have increased user traffic. And in the end, we have relatively few levers that keep these costs in check. So our work at Meta focuses on building at scale observability solutions that we use for maybe landing software optimizations, building our infrastructure roadmap both on the hardware and the software side, and doing model co-design with scale and performance in mind. So our presentation is structured according to our four main layers of observability. My colleague Hao is going to cover telemetry and monitoring. Riham is going to cover application tracing and instrumentation, and Lee is going to cover Meta Performance Profiling Analysis Platform. In the end, I'm going to close with a few examples on how we do fleet-level aggregation, how we do regression tracking, and how we fix those regressions. Next, I'm going to hand it over to my colleague Hao to talk about telemetry and monitoring.
Thanks, Valentin, for sharing the intriguing problem statement and outlining the AI observability stack. I'm Hao, and I work at Meta for 4 years. I mainly work on telemetry and observability with a focus on ASICs. In this section, I'll be giving an overview of the telemetry and monitoring layer. So over the years, Meta has grown exponentially to encompass 21 data centers. This has made telemetry and observability not only an indispensable prerequisite for our services to run reliably and efficiently, but also a challenging problem to solve. The question becomes, how can we provide a powerful fleet health and efficiency overview at scale? To that question, we answer with Dynalog, our distributed telemetry daemon running on all Meta fleet. At a 50,000-foot overview, Dynalog serves three main purposes. First, it collects telemetry at the host and the process level and conducts resource accounting at the fleet level. Second, it serves as a server for requests for real-time telemetry queries. Third, it serves as a moderator for requests to profiling tools at the next observability layer. One major challenge of observability at scale comes from the heterogeneity of the fleet. As the computational demand grows with the complexity of AI workload, the heterogeneity of the fleet also increases with the deployment of various ASICs, including MTIA, which is Meta's training and inference accelerators, third-party vendor ASICs such as GPUs, inference accelerators, video transcoders, encoders, etc. To address these challenges, Dynalog generalizes the metric collection and configuration through LibSigMon, our platform-agnostic framework for AI accelerators. LibSigMon hides the complexity of interacting with individual vendors and firmware APIs through a generalized layer and data flow, and thus providing a scalable way of surfacing key AI efficiency metrics all the way to the top of the observability stack. Next, we want to answer how to make the signal powerful. The bare metal device and utilization metrics have an unexpectedly strong indication of efficiency when used in good combination. We surface device power, utilization metrics at multiple granularities, good put metrics such as flops per second. Combining these metrics, we are able to provide a strong signal for efficiency and model complexity at very minimum overhead at scale. Using GPU as an example, we surface the GPU utilization, which is the percentage of the time the GPU device is being active. SM utilization, which is the percentage of cycles the streaming multiprocessor within the GPU that are active. SM occupancy, which is the warp level parallelism within the SM. And GPU power. We derive flops per second from tensor core and floating point unit utilization based on a heuristic estimation. This basic set of metrics at the fleet level provides a well-rounded interpretation of what the workload is doing well and what has noticeable red flags that we should use the next observability layer, profiling tools, to precisely deep dive. Besides Meta infrastructure, we also extended our telemetry support to the open source community. Fair Research Cluster and Meta Lab machines are already benefiting from this observability, with Research Supercluster as our next step customers. With that, I'll hand over to Riham to talk about profiling introspections at the next observability layer.
Thanks, Hao. Hi, everyone. I'm Riham Selim, and I'm software performance engineer at Meta, where I work on building end-to-end profiling tools for our CPU and GPU profiling workloads, especially for our training and inference workloads. In the previous section, Hao talked to us a little bit about how we do telemetry collection for our fleet. In the next section, we'll talk a little bit more about how we do performance debugging and introspection into various performance issues. As we know, system performance is always the result of interactions across different layers on the stack. For example, on the CPU, we have the CPU workload, we have the CPU activity, off-CPU activity, IOPS, network, and so on. Then we have interactions between the CPU or the host and the GPU or the device, where we could be copying memory between the host and the device, requesting kernel launches, doing memory allocations, and so on. And then finally, we have our device or GPU, where we're doing executions of different kernels or doing memory operations. To get a holistic view of our system, we need to understand the performance across all of these layers and how they work together. That's why we need to build a holistic end-to-end view. And in order to be able to do that, we employ different profiling tools. Let's talk a little bit about some of these tools. The first tool we're going to talk about is Kineto. Kineto is an open source CPU and GPU profiler. It can provide information about hardware performance counters or build timeline traces. It is built on top of NVIDIA scope-T. We'll be talking a little bit more about Kineto in our blog post. For PyTorch-specific workloads, we rely on the PyTorch profiler. PyTorch profiler allows us to understand the memory and compute cost associated with various PyTorch operations. We'll also be talking a little bit more about it in our blog post. The last tool we're going to talk about is Strobe Light. Strobe Light is a daemon that's running across all hosts and Meta fleet. It has a combination of different profilers like CPU profilers, memory profilers, and so on. Most of Strobe Light's profilers are built on top of a kernel technology called BPF. In a nutshell, BPF is a kernel technology that allows you to run user code in a privileged context, like the Linux kernel. By attaching to interesting events, like for example CUDA kernel launches, CUDA memory allocations and freeze, or PyTorch memory allocations and freeze, we can associate these events to understand where we are leaking memory, get the stacks of different operations, or understand the sizes of our memory allocations. Now that we talked a little bit about the different profilers, let's talk about how we automate the collection of these traces. The first step is orchestration. Orchestration is a step at which we decide which profilers we want to run on which hosts and which processes. This can be based on different things. For example, we can decide to trigger profiling based on certain interesting events, like a memory event, or we can decide to do it because another tool requested it, or it can even happen based on a schedule. In all these cases, the orchestration phase is responsible for deciding which profilers to run, make sure that they run in synchronized manner, and send a profiling request to all of these profilers. Once the profilers receive the profiling request, they start collecting the data from the host. Each profiler will run independently, and then we'll upload the profiling result into a common store. That's where we do the stitching. Stitching is the phase at which we collect all of this data that we collected from the profilers and stitch it together in a way that makes sense, based on the timeline of the events and the types of events. Finally, we can use this data for visualizing the timelines, or for detecting some bad patterns, or even for doing statistical analysis. This helps us have an end-to-end view of our system. For example, if you look here, you can see that at the very top we have a timeline of the outstanding allocated memory. Under that, you can see the CPU stacks, and then finally you can see the GPU operations. You can connect these events to understand which CPU stacks led to which GPU operations. Also, using these stacks, we can compare two different points of timeline to understand some regressions. For example, by collecting the memory allocation at a certain point of time, comparing it to a different point in time, you can actually understand where exactly you caused the memory regression. Next, Tian is going to talk to us about Meta Performance and Profiling Analysis Platform.
Thank you, Riham, for the excellent overview of the profiling infrastructure at Meta. Hello, everyone. My name is Tian, a software engineer at Meta focused on improving fleet-wide GPU efficiency across all our services for both training and inference workload. In the following section, I will provide you an overview of a Meta performance profiling and analysis platform, a homegrown, state-of-the-art platform that machine learning engineers and performance engineers use to improve model performance and efficiency. What's Meta performance profiling and analysis platform? It's an automated, one-stop shop, self-service platform for profiling and analyzing AI workload performance. It starts with the idea of profiling as a service and then evolved to become a platform focused on usability. The platform has been seamlessly integrated into Meta ML development and production environment to deliver smooth user experience. The platform has a few important features. Auto profiling. Our platform has been integrated into many training frameworks, so it's able to automatically provide GPU training workload on the entire fleet. In case there's a need to debug performance regression in the middle of training or the workload without the support auto profiling support, the platform is able to collect profiling data on demand as well. Auto analysis. The platform also automatically analyzing profiling data and generates insight from analysis reports. For example, as GPU traces are known to be the most common way for AI performance analysis and debugging, our platform automatically runs trace analysis and reports performance bottleneck and issue found. End-to-end performance observability. The platform not only covers the most important part, the training step, but also provides the performance observability of the data loader, as we found that data starvation is one of the common performance issues seen in production. The observability support of checkpointing will be available soon. Now let's get into the details about how the profiling data is collected. This diagram shows the interaction between our platform and the GPU host running the targeted training job. Basically, performance profiling service receives a profiling API call from a training framework. It downloads the traces of the targeted job from a predefined object store. In the meantime, it reads host metric, GPU metric, and network metric from data sources stored in relevant time series telemetry tables. Once all the profiling data is collected, performance profiling service writes performance data into its performance DB. Then users are allowed to check profiling data from profiling report through performance profiling user portal. As shown in the bottom of this diagram, our platform adopts a four-step approach to profile, analyze, and extract performance and efficiency insight based on the profiling data. Finally, using the insight, we generate a clear and self-serving actionable recommendation for users to review and take action. You may wonder what a profiling report looks like. I will give you a few examples. Here is one example performance overview page generated by our platform. The overview page presents top-line performance metrics and collected traces given a profiling job. These top-line performance metrics are collected either from hardware via the telemetry infrastructure as aforementioned, like GPU power draw, SM utilization, tensor core utilization, or GPU visit time and GPU computation and communication overlap degree through automatic trace analysis. The top-line performance metrics are meant to give users a basic understanding of the performance. The higher, the better. We also highlight performance and efficiency issues found, as one example marked in red. Max GPU memory utilization is low. This page gives an example of GPU metric timeline view for the SM utilization metric. A timeline view of the metric is very useful to spot performance variance and regression along the timeline. Here in this example, we observe periodical drop of SM utilization, a typical performance pattern that could be caused by model checkpointing. Additionally, the timeline view also helps find imbalance among GPU workers. Typical examples include load imbalance from the timeline view of the SM utilization as shown here. Another feature of the platform is the integration with holistic trace analysis. Holistic trace analysis help detect common Anki patterns seen in recommendation models, like load imbalance among GPU workers caused by imbalanced sharding plan. That a GPU worker needed to serve more embedding table lookup operations than others, which caused itself to become structural in synchronous distributed training. Much-rank timeline view in holistic trace analysis provides a holistic timeline view of activities happen on all the GPU workers for the same training iteration. We can use it to easily find the struggler worker. As shown in this example, rank 0 takes a much longer time on the embedding lookup kernel than others. This leads us to further examine its embedding sharding plan. Holistic trace analysis also outputs the input about the GPU kernel time breakdown for every GPU worker. You may refer to our blog. Next, I will hand it over to Valentin.
So the final section is about fleet-wide aggregation and regression tracking. My colleagues presented briefly the capabilities of our telemetry and performance introspection solutions, which we run at fleet level to generate very large data sets. So we have a database with telemetry counters, another database which holds workflow traces, as well as we have data sets that describe the jobs. So we can combine these data sets, aggregate the data, and display it on dashboards, which in the end they guide optimization work or road mapping for both hardware and software. And here are a few examples of the reports we support today that we will briefly discuss in the last slides of this presentation. For example, we can provide a distribution of accelerator cycles by compute time, essentially tell where each of our very hot kernels spend their time. Where are our system hours being spent to identify models that have a very large capacity footprint? Which are the hot operators? And if we have any regression in the execution time of hot operators. Here we have a visual model on how we interpret system hour distribution. We have an attribution per product group, per model, per user, and also per job on the right-hand side. But we also have an aggregation per trainer framework like PyTorch Lightning, Detectron2Go, FairSeek, which are open source frameworks, on the left-hand side. Our goal is to maximize the return of investment in our optimization work, because in the end we have the goal of running more jobs within the same capacity footprint. So we really need to choose carefully what we optimize for. In general, most frameworks optimizations provide rather small magnitude or incremental gains, but the advantage is that they apply to a whole class of applications. However, there could be cases where optimization work on large footprint models can yield up to 2, maybe 3x QPS gain, and because of the magnitude of the gain, they can provide capacity pressure relief in the short term. So based on the aggregation data and the complexity of the work required, we need to make a decision. But we do try to generalize as much as possible the optimizations, and we want to turn them into horizontal ones that impact more applications. Here we have some main reports that come out of fleet-level trace analysis. On the left-hand side, we have an example on how accelerator cycles are being distributed among operators with different compute specific. The diagram is indeed GPU specific, and the slice sizes don't reflect our actual production data. We have the capability to see how many cycles we spend doing in things like matrix multiplications, embedding lookups, normalization, etc. This data tells us what are the categories we want to optimize for, how to do better co-design of hardware platforms, and according to the needs of our workflows. On the right-hand side, we can go one level of detail deeper, and we have the capability of filtering based on production workflows, maybe using a date range, a product group, or a model type, and select various aggregations to identify the top operators that consume accelerator cycles. We can also find template arguments that are really useful because they enable us to evaluate if we can write a specialized implementation. If we can write a specialized implementation, maybe we can reduce the code complexity, maybe we can map that kernel better to the hardware specifics of the platform. As an example, we landed implementations for normalizations, concatenation, and indexing kernels that get called really frequently and run much more efficiently than the default standard optimizations. Here we have an example of a regression detection workflow, and we have cases when operators spike in execution time across the fleet. They do happen very frequently, and they're mainly due to model experiments that tend to be unsuccessful. That means that they usually consume considerable amount of resources, but they don't provide significant model quality improvement. So first, we do monitor the operation duration across time, and we notice if there's a sudden spike. And see in the chart that there's the operator duration was very slow, and suddenly we noticed a spike. Then we can use our dashboard to group samples by maybe job ID, and we can see that we have jobs that have similar model complexity, but some of them show a reasonably high duration on our target operator. So for example, in the table on the right-hand side, we have a job that has pretty much the same model complexity as the other two, but the average kernel duration is up to 15 times higher. So definitely we want to inspect that job and see what's going on. So we look at the job and identify anti-patterns. The final step is to talk to the ML engineer and to evaluate a bunch of QPS improvement techniques, look at model quality, and see if we can land the diff. In this case, with the spike in the normalization operator, we just found that the ML engineer was using a very large layer normalization that wasn't really bringing any benefit to the model quality, so we just removed it and got almost like 4x QPS gain. Observability solution is constantly evolving, and here we've listed a bunch of next steps that we are considering. And I guess the most important one is improving the actionability and recommendations that we provide with our tooling. Maybe we want ML engineers with little or no performance background to be able to self-serve, use some of the findings we get with our observability solutions, and be able to optimize the QPS of their jobs on their own. We hope you enjoyed our presentation, and we are looking forward to your questions. Thank you.